Hello everyone, welcome to Multivariate Statistics and Machine Learning. In this video our topic will be graphical models. Graphical models are a very large area by themselves, so we can only cover basically just the essentials of graphical models, but hopefully you find it interesting enough to study this topic further. So if you'd like to study the content that I will present in this video, then go to section 5.3 in the lecture notes. So what are graphical models? So graphical models, basically, so the purpose of graphical models is to provide a probabilistic model to describe dependencies among variables. Dependency structure. That's the very broad outline, and they do this basically by providing a language to model the joint distributions of the random variables. So we have, let's say, random variables x1, x2, and so on. So these are our random variables, and we have a joint distribution with density fx1 and so on. Let's say it's d. And the graphical model provides a way to structure the joint distribution. So the graphical model you have a structure, so you'll see what I mean later. So we have a structured distribution, and it's the purpose of a graphical model is basically to provide a language so that you can immediately see from this graphical model what is the underlying joint distribution and what are the conditional dependencies and independencies. So it's basically a way to describe structured joint distributions. And since this is what I'm saying is very general, you will realize that basically all models that we've been discussed so far, so basically all models such as regression models, classification models, our mixture models, all models discussed so far are actually graphical models, all of them. So this is why we need to be a little bit more specific. But the class of graphical models, that's an enormously big class, and the idea behind graphical models is basically to become aware about the underlying principles representing all these dependency structures. So what it's doing is basically, so people have described graphical models is basically a marriage between probability theory and graph theory. So it's basically because we need graphs to describe the dependency structures. So graphs describe structure. So we have a visual representation of our dependencies or independencies depending on the models. So we have graphs, so graphical models. Is probability plus graphs. I mean, in a simplistic fashion, obviously. So, but this points out that we actually need to learn some terminology. So, from graph theory mainly, terminology. So we have a graph. So graph G, and a graph is, mathematically speaking, nothing else but a collection of vertices or nodes and edges. So a graph consists of edges and vertices. So nodes and edge, and they're also called branch, especially if it's a tree. So edges can be directed, so it can be like this, or they can be undirected. And vertices are denoted like this, and they can be internal or external in a graph. And when they are external, then they're usually also called leaf, especially also in a tree. So we can have directed graphs, and a directed graph contains only directed edges. And likewise, we can have an undirected graph. That contains only undirected edges. So later we'll see how we basically use this kind of language to turn this into a probabilistic model. But so we have directed and undirected graphs, and then of course we can have also mixed versions. So there are graphs that are partially directed, for instance, partially directed graphs, and so on. So both directed and undirected edges. So if we have a directed graph, so then we have a relationship. We have parent nodes and child nodes. So we have parent of a node, and that's written PA for parent, and then we have a V for vertex, and we have a child of a node. That's the opposite. So we have, when we have this relationship, then this would be the parent and this is the child. So it's basically just like in a family tree. Then we have certain graphs that are called DAGs or DAG, and that's actually quite an important type of graph, and that's called a directed acyclic graph. So if you have a directed graph, so you can have like nodes like this, and then if you have something that looks like this, that goes where the arrows go in one way, that's a cycle. And basically often in graphical models these are kind of supposed to represent like the influence or like some sort of dependency structure, and if it's a cycle, then sometimes that's not a good idea, because you, for instance, if it would be a time course model, you don't want that the future action influence the past. So we often focus our attention in graphical models on directed acyclic graph, and an acyclic graph has no directed cycle. So that's a directed cycle. And then a special DAG is actually a tree. So a tree is, we have a root node, and then it goes down, it branches off, and so on. So by the way, at each node you can often have 2 childs, but sometimes you have more childs. So then it's a binary tree or a non-binary tree. So that's a tree. So because this is the root and these are the leaves, so it's basically it's upside down. But still called a tree. So that's the graph theory part. So it's not really theory, but like graph terminology. So how how does the probability theory come in? So the probability comes in, basically we have this joint distribution, and then we try to model the joint distribution based on a graph. So let's assume we have a directed graphical model. Let's discuss this first. So a directed graphical model is as follows. So I said in the beginning we would like to model the joint distribution, and the joint distribution would be fx1 xd, and in a DAG the joint distribution is actually relatively easily written down, because you only write down the conditional distributions. So you have a product of your distributions from the parent to the child. So it's basically the product or the probability. If it's discrete, let's write it like this: xi from the parent of xi. So we condition, so we have conditional distributions. So each of these branches, so let's say we have this, the joint distribution is the product of the, so if this is x1, x2, x3, so this is the parent of both x1 and x2. So this would be the probability of x1 given x3 times the probability of x2 given x3 times the probability of x3. So this is our decomposition of the joint density or joint distribution given this graph structure. So we can decompose joint density into products, and these products are really directly determined by the graph structure. So that's the whole point. So the graph is a representation, a visual representation of these products of these conditional distribution. So it's visual representation. Then for DAGs, it's particularly easy to do this. So in these DAGs, so probabilistic DAGs, if you read the literature, they sometimes called Bayesian networks, which is actually, I'm not quite sure why they're called like that, because there's not, I mean, maybe because of the conditionalization, but there's actually not anything Bayesian about it, so I would prefer to call them, it's just a directed acyclic graph that has a probabilistic underpinning. So now all the methodology in graphical models focuses on how to learn the graph structure and the associated probability distributions from data. So basically we need methods to fit the distribution, because once we know the distribution, we know the underlying DAG or underlying graph in this, DAG in this case, but we would like to know the graph, we would like to know all these conditional distribution, and then we can learn something about the model. And of course, as we've seen in this course already, in other courses, there are some standard methods you use to fit these methods, like maximum likelihood or some Bayesian inference, and that's how you typically do this. But the problem with graphical models, of course, or generally the problem, if the more variables you have, the more complicated the whole thing becomes. And in fact, the whole reason why we're using graphical models is that we're trying to simplify this process. So because by imposing some of the structure, we can simplify the problem. For instance, by assuming that we have a tree structure, we already reduce the space of the models substantially. So we need methods to fit the distribution, and then we have graphs, and then we have somehow we need methods to explore the space of the graphs. Space of graphs, or basically models. And that's actually something that's the difference between the models we've discussed so far, because we only looked at always at one model and we fitted one model to the data, whereas in graphical models the type of model is usually the aim. So you need to find through, or you need to do the fit for each individual model, and that can be computationally really, really expensive. So so we need to do typically what is done. So there's no easy way around this, so you need either some stochastic search or some heuristic approach. But it's typically an NP-hard problem, so you can't, there's no shortcut. Maybe quantum computing sometimes, maybe, I don't know. So the third thing is sometimes the internal, so we have models, give graphs, and we know how to fit them. So this with the usual methods, usually maximum likelihood or some Bayesian thing. We have this computational problem that we have so many models. And then one thing that's kind of links with both of these themes is that, for instance, in graphic models we have a lot of latent variables. The latent variables are not directly observed variables, and these correspond to typically to internal nodes in the graph. And in a DAG particularly, there are some tricks to speed up the computation. For instance, if you want to compute the likelihood, and you can do it in a naive way and you can do it in a clever way, and so there are some algorithms to speed up the computations. For instance, one algorithm that you probably might have heard is the Viterbi algorithm. And that's basically a way to do, when you say you have a tree-like structure, then you can compute the likelihood function, for instance, by some recursive algorithm. So there are lots of algorithms. So graphical models is not a pure mathematics field, I would say. It's like you need to learn a lot about algorithms. So this is why I can only briefly touch this here. And especially with directed graphical models, you do need to find some clever search algorithms to search through all the to the enormous space of these models. So in the references, or in the lecture, I gave you a reference where you can look up further information about some books where you can read more about this. So for references for books on graphical models, there are some very good ones. And see the script. So there's I have some suggestions there. So, but the key thing is what you need to remember: if you have directed graphical models, then the directed graph basically decomposes the joint distribution into a product of conditional distributions. And these conditional distributions, they are the elements that make up the graphical model. So now we've talked about directed models, so we can also talk about undirected models, and they're actually a bit, I mean, they're closer to what we've been discussing in this module. So undirected graphical models. So in directed graphical models, it was kind of clear what the edge is meaning, namely that you condition and then you define a relationship between a parent node and a child node. For undirected graphical models, we need to think about different definitions of what the edges actually mean, and a common use is to define an edge, the presence of an edge when there is a conditional dependence, and the absence of an edge when there is conditional independence. I mean, that's actually the same for directed graphs. And for undirected graphs, we can use this conditioning also to define the product density as follows. So we have our let's let's say, so we have our set x1, xd is our set of random variables, and we pick two variables, xi and xj, and then we can say that xi is independent of xj given the other variables. So these are all the other variables. So these are all other variables. So xi is independent. So x and xj are conditionally independent given xk. So this is what this means. And these kind of independences we would like to model by a graph, and we modeled it by the following principle. So we have our joint distribution again. So the joint distribution would be for all these variables, and we can write it as follows. So the joint distribution is simply the product of the xi, so this is one node, given the other variables xk, times the product of xj given all the other variables xk, times the probability of the joint distribution of the k. So it's not so, I mean, it's actually similar to the directed graphical case, only that we only focus on two. We pick two, and then we can find the conditional distribution, and then we can write the joint distribution as a product of these three distributions. And the key thing is now we can actually do it not just in one way, we can do it basically for all pairs of I and j. So you can also write this in a slightly different way. So you can say that the conditional distribution of xi and xj given all the xk is the product of the conditional distribution. So you can see they're actually conditionally independent because they're just the product of these conditional distributions. So this is so that's equivalent. And so for undirected graphs, there's also a way to factor the joint distribution. And so this is factorization of the joint density, and for the graph, in an undirected graph, a missing edge, so if we don't have an edge, missing edge corresponds to conditional independence. So give an example. So we have a couple of variables, and then we can have a fully connected graph where everything is connected with everything. And if we have one, so of course this, and if we have one edge that is not connected, for instance, then these two would be conditionally independent given all the others. So that's the interpretation. And now, so that's quite theoretical, but now the miracle or not miracle, but the interesting thing about undirected graphical models is that there's a close connection with Gaussian graphical models. So the Gaussian, or with conditional independence for normal model. So if you have a Gaussian graphical model that's called GGM normally, then we assume that the variables x are multivariate normal. So we have a mean vector and a covariance vector. And now there is the following property. So I'm just stating the property. So we don't have, as I said, we have only like very, very little time in this program here to describe this. So the whole point about this is, so we have multivariate normal data, and then if we look at this is the covariance matrix, and the covariance matrix, if we invert this covariance matrix, we get the precision matrix. So that's the precision matrix, and that has components omega ij. So this is omega, and so it's a matrix, and this is the matrix inverse, and these are the elements of this matrix. And now the interesting thing is that, talking about conditional independence, so conditional independence, if the element of this inverse precision matrix is equal to 0, then xij is independent of xj given all other variables. So, and it actually goes both ways. So that's called a conditional independence model, or covariance selection graph. So covariance selection graph. So there's many names, but that's basically the key feature of the multivariate normal. When there are zeros in the precision matrix, that corresponds to independence of the conditional independence. So zeros in corresponds to conditional independence. And that's why GGMs, or covariance selection graphs, are so popular, because the only thing you have to do to get this network is to compute the covariance matrix and then invert the covariance matrix. So recipe to infer a GGM is very simple. Step 1, estimate sigma to get sigma hat, and usually you do this for large samples in maximum likelihood, or you use some shrinkage approach. Then second step, you invert this thing, and in fact you could actually also directly estimate the inverse. So basically one step. Then you find the zeros, in omega hat, and then you draw draw graph. Basically, you draw the graph by leaving out edges where there are zeros. So no edge when there are zeros. So how do we actually interpret the whole thing? So of course we can interpret it in terms of conditional independence, but there's also another interpretation that's closely linked to this inverse here. So there is something called the partial correlation. So partial correlation is defined as follows. So you have a correlation between I and j given all the rest of the variables, and that is defined as minus then the omega ij, so the inverse precision matrix element ij divided by omega ii times omega jj. So this looks like the definition of correlation except for the minus sign. So similar definition of Pearson correlation. So rho ij given the rest is this thing here. So it's basically just proportional. It's a standardized precision matrix. Whereas correlation is of course a standardized covariance matrix. So p-core standardized precision matrix, and correlation would be standardized covariance matrix. And so in a GGM, the intensity, so each graph has each edge has a number, and if there's a number missing, means that basically there's zero partial correlation between any two variables that are conditionally independent. So missing edge in a Gaussian graphical model means zero partial correlation. And one interpretation of partial correlation is that you keep, I mean, not one interpretation, that's basically the interpretation. So you keep the variables fixed, and then it's basically the correlation that remains between those two variables if all the other variables have been taken into account. So p-core is correlation that remains if all other variables have been regressed out. Into account. And in fact, you can define correlation by you take your variables xi and xj, then you regress them onto the remaining variables, and then the partial correlation is basically the correlation between the residuals that are left after removing the influence of the other variables. So partial correlation is easy to interpret, not just in terms of conditional independence, which of course, because we're operating in a normal setting, so the independence and uncorrelatedness is of course the same, but not in general. Okay, so in the script you'll see an example for this. So example, and I'll show it to you briefly, and then in the worksheet you do another example by yourself. So let's go to the example. So that's a famous example actually from a very famous textbook. So this is some exam score data. So you have several subjects, and you can see here the correlation between the subjects or the exam results. And so we have mechanics, vectors, algebra analysis, and statistics. And the question is, which students perform, how do they perform, or is there any relationship between subjects? And here you see the, like, just the normal plain correlations. So there's not much to see here, in effect. But when you look at the partial correlation, so you take the inverse of the correlation matrix and then you standardize it, you get this thing here. So you get actually some areas where you have almost no correlation, either zero or almost no correlation. And in total there are 4 of those that are small. And so there are actually some statistical tests to do this, but you can see that analysis and mechanics, statistics and mechanics, analysis and vectors and statistics and vectors are conditional independent. And so for 5 subjects or 5 nodes, there can be at most 10 edges, and 4 of them are actually missing. And the conditional independence graph, taking account of all these missing edges, looks like this. So you can actually write it like this. So you can see that knowledge of algebra is actually linked to all of these other subjects, but some subjects are not directly connected, for instance statistics and vectors. And that's probably true only for I don't know what statistics class this was, but definitely in multivariate statistics I would think you would need a lot of vectors and matrices. But this is how this for this particular data, what the result is. In the example sheets you will have to compute your own network for some other data sets. Okay, so that's it for this topic. So unfortunately this is really such a big topic that it's almost impossible to do justice to this subject, even in a short review like this. So I highly recommend, if you want to study this further, to look up some specialized literature on this, and then to see how the framework of graphical models fits into statistics in general and also into machine learning, because it's just a pervasive thing. So everything there in machine learning and in statistics, I mean, I don't know of any model that cannot be cast into the framework of a graphical model. Okay, so that's it for today, and I'll see you in the next video. Bye bye.